So continuing where we left off, we talked about our fighter pilot. I showed you a couple other examples of videos where it was clear, that the velocity was tangent to the radius. We saw some bad physics videos. And so the question is, how do we calculate acceleration? The proof is long and cumbersome. It's neat, but it's a bit long. For the first time in a long time, I'm just going to give you circular or centripetal acceleration, and I usually abbreviate that A with a little subscripted c. Turns out to be v squared over r, where v is your circular velocity tangent to the radius. Okay? Oh, and r is the radius. So if you double your circular speed, 4 times the circular acceleration, 4 times the force, for what it's worth. This is why rides that move in a circle, you feel such a tremendous force acting on you, even though in terms of a car driving, you're not traveling that fast compared to a car driving. It leads to the next question. Okay, how do you calculate circular velocity? Or I guess I should say speed. The velocity is always changing direction. It's always perpendicular to the radius. Well, I know that v, if you're not accelerating, is distance over time. It's d equals vit plus a half at squared, but Rachel, if a is 0, the half at squared vanishes, and I just got the v by itself. Now, what distance? And the answer is once around the circle. The fancy word for that is the circumference. What's the equation for the circumference of a circle? Yeah, it's actually on your formula sheet. By the way, pi r squared is the area, so it's the other one. Two pi r. That's once around the circle. That's your distance. And then we use a special variable for the completion of once around. It is a time. It is measured in seconds. We use a capital T. A capital T is called the period. I snuck this in a wee bit in Physics 11 way back in the day. It's going to become used way more in this unit. Which means circular speed is 2 pi r over the period. It's not on the sheet, but really it's v equals d over t, meters per second, in disguise. What's meters in a circle? The circumference. What's seconds in a circle? Once around. So I will ask you, maybe on a test, to find a circular speed. This is the equation that's not on the sheet. However, it seems to me I could plug that in there and get a new equation, and we will shortly. Another concept closely related to period is the frequency. The frequency is the number of cycles per second. Period is the number of seconds per cycle. Frequency is the number of cycles per second. Period is the number of seconds per cycle. Frequency is the number of cycles per second. They're reciprocals of each other. The unit, cycle per second, is also known as a hertz. So again, period is measured in seconds. Frequency is measured in hertz. We see they're inverses of each other. What that really means is if you know the frequency, sorry, if you know the period, you automatically know the frequency. It's 1 over the period. Or if you know the frequency, it's 1 over the period. Sorry, the period is 1 over the frequency. They're reciprocals of each other. Is that on the formula sheet? I can't remember. Under circular motion, you have to turn the page, find the circular motion section. T equals 1 over f. Okay, and I expect if you know that t equals equal to 1 over f, it's 1 fraction equals 1 fraction, stuff moves diagonally. Okay, so that is on there. One version anyways. So, example 6. This is where circular motion gets a little weird. Okay? An object is moving at 4 meters per second in, what did I underline, Ryan? That's important. Okay? What uniform circular motion means is constant speed around the circle. You are accelerating inwards, but that's circular acceleration, and that's different. So it accelerates at 2 meters per second squared for 30 seconds. Find A, the final speed of the object. This is a trick question. Why is V final 4 meters per second? If you're moving in a circle at a uniform circular motion, your speed isn't changing. Now, a lot of kids want to go, oh, VF equals VI plus A times T. The A is not in the same direction as the velocity. You can't plug it into that equation. It's a vector. It's completely different. There is an acceleration inwards, but that's not changing your speed. It's changing your direction only. So it's a trick question. So easy that it's tough. B, the distance traveled. Well, the distance is really the circumference. I'll even write that word out. So the distance around the circle is going to be 2 pi r Well, we got to be careful. Cross that out. We got to be careful. Sorry, I shouldn't have crossed it out completely. Again, I can't use my standard kinematics approaches here. The distance traveled, I can use, okay, the distance is going to be in this direction, in this direction, in this direction, oh, bad drawing, in this direction, in this direction. What's the distance going to be? The distance is going to be that. Circular speed times t. Wait a minute, Mr. Dueck, shouldn't it be plus a half at squared? Look at the direction of the acceleration. Look at the direction of the velocity. Are they in the same direction? So don't be putting the a in here. It's just going to be straight. You know what? You're traveling at 4 meters per second for 3 seconds. You traveled 12 meters in a circle. You traveled for 12 meters. Now, I already told you this, and I already told you this. I told you that AC, centripetal or circular acceleration, is v squared over r. And I told you that circular speed, and you'll notice I'm not putting vectors on any of this stuff because the direction is changing constantly. They are vectors, but I'm only finding magnitude right now. For me to give you a direction, I would say, Logan, show me a picture, please. Okay? If I plug that into there, I get this. AC equals, well, it's all going to be over r, but I'm going to get 2 pi r over t all squared. Okay, Jake, what's 2 squared? Don't overcomplicate it. What's 2 squared? What's pi squared? You know what? I'm just going to write pi squared. We have an r squared over t squared. And then what else is on the very bottom? Which really just means it's on the bottom there. Oh, how many r's on the top? Do you see it? 2 on r squared. How many on the bottom? Okay, you know what? This is another, boy, say that carefully. This is another equation for circular acceleration. We're going to write it in the box. And it's also on your formula sheet. It says this. There are two ways to calculate circular acceleration, and it depends on what you know. It's either 4 pi squared times the radius over t squared, or it's v squared over r. I'll be honest, Sam, when you do, by the way, I'm in the process of registering us for Playland. It's probably going to be Tuesday, May the 12th, I think. It's going to be a Tuesday. At Playland, when you're trying to calculate the acceleration of a ride that moves in a circle, you won't know how fast the ride is traveling, but it's pretty easy to time how long it takes to go once around. You'll know the period. This is the one I use most often in quote-unquote real life. Having said that, Justice, is going to be sometimes when I give you the velocity, the circular speed, and you can use the v squared over r. So either, if you know how long it takes to go once around, it's 4 pi squared r over t squared. That's the acceleration. Oh, if it takes you less time to go once around, do you feel a bigger acceleration or a smaller acceleration? Bigger. How would it take you less time to go? You'd have to be going faster. Oh yeah, if you go faster, I feel that force. I'm assuming you've all been on at least one ride that goes in a circle, and you've noticed as you speed up, your inertia makes it feel like you're getting pushed out more, and well, actually, you're feeling an acceleration inwards more and more because it's the door that's what's applying the force to accelerate you inwards, but you think that you're pushed outwards. Those are the big two new equations for this unit. The two ways to describe circular acceleration. But Ty, if I know the acceleration, I can also then go and find circular force, which we're going to spend a lot of time talking about. You don't need to write it down yet. We're going to go on a big song and dance. So, let's summarize. AC equals v squared over r. Also equals 4 pi squared r over t squared, where t equals the period in seconds, r equals the radius in meters, and v, well, you can calculate it if they don't give it to you. It is 2 pi r over the period, and it is the uniform circular speed, constant speed. So what that means, Atla, is in uniform circular motion, we got a strange situation. The object is moving at a constant speed, but it's also accelerating. Why? Because, Halen, its direction is changing, not its speed. Oh, and the acceleration vector is constantly changing in direction, and it's never going to be in the same direction as the velocity, which means we cannot use our constant acceleration equations. What we have to use are the ones for uniform circular kinematics. AC equals v squared over r, or 4 pi squared r over t squared. V equals 2 pi r over t. Oh, you can still use distance equals v times t. That's fine. You can also use v average times t, although I hardly use those last two. Hardly ever. Okay. Homework the first. Homework part 1. For the Earth rotating on its axis, oh, if you look on your data sheet, you're going to be using your data sheet, this unit, a great deal. Let me go back to the very, very beginning now. I think I have it here somewhere. Yeah. So you're going to be using very often now the Earth's radius and, what's the Earth's period of rotation? How long does it take the Earth to go around once? Please tell me you know this. 24 hours times 60 minutes times 60 seconds. Although, holy smokes, they actually crunched it for you. So if I go 24 hours times 60 minutes times 60 seconds, of course I should get 8.61 times 10 to the 4. I don't get 8.61. What's going on here? Now, I use this one, but they're being correct and very, very... So, rotation is defined as how long it takes for you to arrive back where you started from, right? Okay, people at home aren't going to be able to see this, but I'll leave the video running anyways and I'll talk really loud. Is yours standing still? Is yours standing still? It's also moving around the what? Sun, okay? So, if I'm spinning this way, and I'm moving around the sun, so I'm going to start out facing Lisa. This is going to be how long it takes me to get around once, and I'll stop when I end up facing Lisa. Am I pointing in the same direction as I was before? Ah. So they are using the how long it takes before you're pointing back at the sun at the same time. We're going to use 24 hours times 60 minutes times 60 seconds. I use 86,400. Having said that, I'll mark them both ways. But the rest is correct. Period of the orbit around the sun, that's 365 days converted to seconds. Radius of the orbit around the sun, we have the period of rotation of the moon. So you're going to be using this data sheet an awful lot. Okay? So, as part of your homework then, consult your data sheet to find the radius and the period of the Earth. Then, on the equator, find the frequency, 1 over the period, the speed, and your centripetal or inwards acceleration. Same thing for the moon. Same thing for the Earth around the sun. Number 4 is good. Number 5 says this: if your car starts at rest and you jam on the gas, your body will seem to be pushed backwards. Which way are you accelerating when you floor it? So why do you feel like you're getting pushed backwards? This is the same phenomena for why you feel like you're getting pushed outwards. What your body is experiencing is its own inertia. It wants to not keep going in a straight line at a steady speed. It wants to remain at rest. And so an object has to apply a force on it to get it to stay with the car. The seat does. It pushes forward on you, but because you're so egocentric, you think everything revolves around you, you think, oh, I'm getting pushed into the seat. No, the seat's pushing on you. Okay. Anyways, we just did number 5 together. 7 is good. Nope, just lost my pen, did I? My back. Irritating. Update. So 7 is good. 8 is good. 9 is good. 10 we're not ready for yet. We're going to move on to lesson 2 because lesson 2 is going to help you with the homework from lesson 1. Trust me. So lesson 2, part 1. Horizontal circles. We're going to divide circular motion into 2 main types: horizontal circles and vertical circles. Vertical circles are tougher. We won't deal with slanty circles. So let's go back to Playland again. Either the circles that you're analyzing will be horizontal, like the scrambler, like the swing. Although the swing does go on a bit of an angle, we're going to pretend it's level. Or it may be a vertical circle, like a Ferris wheel. Or like the Enterprise is the ride that goes in a nice vertical circle. But the Enterprise also at one point is slanty. That's yucky physics. We're going to leave that alone. So I'd like you to imagine that you're in a car turning a corner. What's the direction of the acceleration? And what's the direction of the net force that acts upon you? Let's do the first part. I've tried to convince you. If you're turning a corner, moving in a circle, what's the direction of the acceleration? So, you know what? I've given you enough of these chart questions on your tests that I've taught you. Put a check mark next to the answer that you think is correct. Is my pen going to stop working again? Okay, pause the video again for a second. See if it fixes itself. So let's use my check mark and X's. Yes, yes, no, no, C and D are wrong. What about the force? Well, I'm going to give you a hint. F equals what? Now, force is a vector. Is mass a vector? No. Is acceleration a vector? That's where force gets its direction from. So if your acceleration is inwards, again, what direction do most people think the force is? Outwards, because they're confusing their own inertia, Newton's first. They're confusing that with a force. Explain your answer using principles of physics. We just did. In Latin, the word centripetal means towards, pedal, the center or center seeking. So when an object is moving in circular motion, it has inwards centripetal acceleration. Oh, and by Newton's not by Newton's second law, by Newton's first law, if you have an acceleration, there must be an unbalanced force in the same direction as the acceleration. So an object moving in a circle has an inwards force. So I like to use the following notation. For the rest of the year, if you see that, I'm talking about Unit 2 straight line forces. If you see that, that's centripetal force. F equals ma. Fc equals mac. By the way, what this really means is Fc equals either mv squared over r, that was one of our equations for A, or moving in a circle, the force, the centripetal force is m4 pi squared r over t squared. Logan, the most common sloppy, I'll even use the word stupid mistake that kids make, because the accelerations, Logan, have so many are complicated, I see kids do that. They forget the m. Well, I'm sorry, force and acceleration are not the same thing. They're only the same thing when they're multiplied by the scalar mass. Don't do that. So I almost always will write this and then go further, just because I don't want to forget the m. Second key. We're going to be doing winner minus loser again. Sam. This is hugely important. In our winner minus loser approach, the centripetal force will always be the net force. What does that mean? It will never actually appear on a free body diagram. It's always going to be this thing. And recall when we did our winner minus loser, the MA never actually appeared on our free body diagram. All the subforces that were causing that one uber force did. When you're moving in a circle, you're never going to put FC on the diagram. It's always the net force. Show you what I mean. A car is approaching a circular turn that has a radius of 60 meters. If the coefficient of friction between the car and the pavement is 0.45, what's the maximum speed that the car can safely travel through the turn? I like this question, I like this question, I like this question. Also, it's a useful question, too. So if you've seen when you're driving and you're approaching a turn, a corner, and you've seen a speed sign showing a lower limit, this is how they calculate it. Okay? We're going to go... And then we're going to go okay? Here's the car. Say it's traveling. You know what? Let's have it traveling instead of that way, Mr. Dueck. Have it traveling this way. What are the forces acting on it? Get the obvious one. Gravity. From the top view, I would draw that into the page. Is it sinking into the ground like quicksand? Is it flying into the air like Superman? Why? What's pushing out of the page? What's keeping it from sinking into the ground like quicksand? Okay, so I'm just going to say, because it's tough to draw, I'm going to write that. What else? What path is this car tracing out? A circle. There must, therefore, be a force. I'm not going to call it FC. What's pushing it in a circle? What pushes a car in a circle? Why is it so hard to turn on ice? I said side view. You know what? What I really mean is front view. Here's the road. Car is coming out of the page right towards us. Okay? This is how it's always drawn. This is how we're going to visualize it. Now, it's turning in a circle. Oh, Mr. Dueck. Well, it's kind of turning. Don't write this down. I want to show that it's turning this way. So here's how we do that as well. What we do is we put a little pole like an axis of rotation, and we go like this around it. That's our way of saying it's coming around that way. We add that, in this case, to the left based on my drawing. What are the forces acting on the car? Get the obvious one. Right? What path is this car tracing out? A circle. So there has to be a force towards the center. Which force? Friction. I don't care which free body diagram method you visualize. Both have their pros and cons. I kind of like the front view better because I can get all three forces on there. But it's more awkward to see the circle part. Here's what I want you to realize. Vertically, all the forces are balanced. What's my only unbalanced force? What's my winner? What path am I tracing out? Winner equals you're moving in a circle, FC. I think it was Vanessa. Vanessa, friction equals what times what? Mu, was it Vanessa in this class? Can't remember. I always picked on somebody. Okay. Mu times the normal force, right? Equals, and now I'm going to write MA, but not A, AC. Okay? I don't know the normal force. Oh, but look. I know another force the same size as the normal force. Which force? By the way, one of the things you're going to notice about the masses in this question is what? This is why trucks can drive on the same roads as cars, and the same roads as semi-trucks, on the same roads as logging trucks, on the same roads as bicycles, on the same roads as motorcycles. Okay? So let's do that. Now, I have two equations for AC. I have this one, and I have this one. Ty, these are both from my formula sheet. You don't have to memorize those two. You probably will during this unit because you get sick of looking it up. Which one am I going to use? Oh, or T squared, thank you. Which one am I going to use? Depends what they gave me. Did they give me how long it took to go around the circle, or did they give me my circular speed? What do they want me to find in this question? Ah, so it's not what they gave me, it's what they want me to find. They want me to find circular speed. I better put in the version of acceleration that has a circular speed. So I'm going to get this. Okay. Get the V by itself. And this is how they calculate the safe speed to go around a corner. It's a little more complicated because this is you're almost ready to slide off the road speed, so they would add a huge safety margin. You'd need to know mu of pavement. They probably add a mu, they probably use a mu based on bad weather. But how fast can this car go around the corner? It's going to be the square root of, what's mu? I don't know, what's mu with you? 0.45? 9.8? Corner has a radius of, what did I say? 60, not 45, Mr. Dueck. What speed limit sign would be, well, again, we wouldn't put this speed limit. This is the maximum speed you can safely go around the corner, so they would never post this sign. But this is how they would calculate what kind of a sign to post. You get 16.26. And then if you wanted to, you know what? 60 kilometers an hour for this particular, no, that's maximum. You'd feel if you were driving at exactly that speed, you would feel very uncomfortable because you could feel that your tires were just about to, you'd feel like you're about to slip off the road. Actually, keep going in a straight line at a steady speed. But you'd feel it through the steering wheel and you'd be going, this is not good. So they probably, you know what? They put a speed limit of 40 kilometers per hour, which is what they do most of the time. Anyways, 16.3 meters per second. A test tube rotates with a period of 9.9 times 10 to the negative fourth seconds. What's the centripetal force on a amoeba at the bottom of the test tube? So I guess we're talking about a little amoeba like right there. What's this question asking me to find? The centripetal force. You know what? First thing I might try, if they're saying find the force, I might just say, well, maybe FC equals MAC. I might say, maybe I don't need to do a free body. Maybe I can just plug and chug and let's see. Did they give me the mass? Yeah. Which version of acceleration might I want to use in this question? The one with the speed or the one with the period? So I'm going to go m4 pi squared r over t squared. And now I'm going to zoom out and I'm going to say, did they tell me the mass? Check. Did they give me the radius? Yeah. Did they give me the period? Oh, okay. M, 1.8 times 10 to the negative 9. By the way, this unit in particular, you want to practice with your calculator. Every year I see kids getting test questions wrong with all the right numbers written down. 4 pi squared times r, 9.9 times, no, where's r? 0.15, all divided by squared. You need to learn how to type all this into your calculator, where the brackets need to go. Can you even type a pi squared? Some of your calculators might force you to go pi times pi. More than one number on the top. Hey, you need to know where your pi button is. Fine. Oh, I got a typo here, Mr. Dueck. I hit answer instead of that. 1.8 times 10 to the insert, negative 9, times 4 times pi squared times 0.15, close bracket, divided by 9.9 times 10 to negative 4, squared. You should get that. If you didn't get that, this is your time to call me and I'll help you figure out how you, or try figuring it out how to type it yourself. Anybody need my help? Okay, pause the video. So I get 0.0109 newtons to 3 sig figs, and it's a force, it is newtons. Now that may not seem like much, but if I wanted to, I could divide by the mass. That's the acceleration. If I divide that by 9.8, that centrifuge is putting about 600,000 Gs on that little amoeba. It's going to get ripped apart. This is how medical centrifuges separate various components. Okay? It's a huge force for an amoeba. Turn the page. And then are we going to get to outer space? Yeah, we are. Cool, 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 cool. Oh, yeah. Example 3. An empty swing on an amusement park ride has a mass of 10 kilograms. If the swing has a kinetic energy of 460 joules, what's the centripetal force on the swing? Okay. What's this question asking me to find? Okay. It's either going to be mv squared over r or m4 pi squared r over t squared. Which one? I don't know. What else did they give me in this question? Ah, okay. What can you tell me that Ke is? You know what? I think I'm going to use the mv squared over r. That's going to be the centripetal force. By the way, what's this right here? What's this right here? I could solve, I could put a 460 here times by 2, divide by the mass. I'm going to algebraically get the v squared by itself. I'm going to say, you know what? This means v squared equals 2 Ke over m. And I'm going to try plugging this right into there. And I'm going to get m over r, and then a 2 Ke over m. There's the v squared. I don't need to square it again because I plugged in a v squared for a v squared. Hey, what happens? Okay. I guess if you're moving in a circle and you don't know your speed, but you know your kinetic energy, it's 2 times the kinetic energy, twice the kinetic energy divided by the radius. It's going to be 2 times 460 divided by 7. 2 times 460 divided by 7. Centripetal force, 131 newtons. 131 newtons. Or if you wanted to actually find the acceleration, divide by the mass. 13 meters per second squared, about a g and a half. This is about right, actually, because the music ride where you swing in a circle is pretty tame. You've been on it. You're not going, wow, I feel like I'm being flung way. Now, the big new one that they put up, the atmosphere, okay, that's a different kettle of fish because your speed is much faster. You have way more kinetic energy. I like example 4. I like example 4. I like example 4. It is a nice question. So let's do some road safety. A car can travel without slipping at a maximum speed of 32 meters per second in a circular path of radius 72 meters on a dry horizontal surface. When it rains, the coefficient of friction is reduced to 1/2 of its original value. What is the maximum safe speed of the car under this wet condition? You know what? I think I'm going to go divide my page. Really, it's frozen again? I'm going to have to really reboot this. I'm going to divide my page in half. When it's dry, when it's wet. Now, I'm going to argue, McKinley, it's going to be the same free body diagram in each situation. In fact, I know roughly how much room I'm going to need there. I'm going to do the free body diagram at the top, and I'm going to do the front view. So here's my car coming out of the page towards me. You know what? Let's pretend let's go have it going around a corner that way. I just know it's going in a circle. What are the forces acting? Oh, you guys are drawing that, sorry. All right, there's the trick to drawing a car. You draw the tires like little rectangles, one big rectangle with headlights and a trapezoid on the top, and it kind of looks like a car. You can figure it out. What are the forces acting on the car? Get the obvious one. What else? Same size. What else? It's moving in a circle. There has to be a force pushing it in a circle. Do not put FC there. That doesn't appear on the free body diagram. What force is pushing it in a circle, Ryan? So in each of these situations, I think I'm going to have this. Let's go as far as we can on the wet pavement, and let's see if we run into a situation where we don't know something. I have a feeling we'll have to go back to the dry pavement to figure it out. Friction is what times what? Mu mg equals m. Am I going to use, do you think, v squared? What are they asking me to find? I better have a speed in my equation then. I'll use the v squared over r. Once again, we can have big vehicles and small vehicles on the same road. Once again, kind of like we had before, v is going to be the square root of what? Mu gur. Or mu rug, or put an R in front. It looks like the word rug. Sure, but I usually put the mu in front. That was Carly's joke. She wants us to do this. No, I say no. Hey, do I know the radius? 72 meters. Do I know G? 9.8. Do I know the coefficient of friction when it's wet? Maybe I can use, let's go to the left side. It's also going to be could I find mu here? Do I know V? Do I know R? Okay. Mu is going to be V squared over gur. And when it's dry, 32 squared over 9.8 times 72. 32 squared over 9.8 times 72. Apparently the coefficient of friction when it's dry is a little ridiculous because I was making up numbers. It's like dragster tires or something. Do you get double check? Is that right? And I did that right? Divide by, yeah, okay. Note to self. Maybe I want to, oh, you know why? Okay. 32 meters per second. If you times that by 3, this is like 120 kilometers per hour over a very small radius. This is turning like, wow, you're really turning, cornering well. So I made up some bad numbers. Note to self, I may put, you know what, I should put a 1 in front of the radius or something like that. Then it'd be better. But for now, we're committed. So I get a mu of 1.451. How's that help? When it rains, what happens to the coefficient of friction? So it's going to be 0.7256. Times 9.8 times 72. Now here's what I want you to notice. If it's half as sticky, if mu is half, the speed doesn't go down by half. The answer is not going to be 16 meters per second, I don't think. You get 22.6? Okay. This is why there's fewer accidents when it's slippery than there should be. When it gets slippery, you do need to slow down, but it turns out it's not a one-to-one relationship. If it's twice as slick, you don't need to go half as fast. Although you should for safety. What did I say? 22.6 meters per second. A little bit more, and then I'll give you the rest of class. Technical comment on turning. The reason friction is inwards has to do with how wheels work. Okay? When you turn your front wheels to turn the car, Newton's first kicks it. Car wants to keep going straight. So that means because the car wants to keep going straight, but you've turned the wheels apply a force this way to the road. What does the road do? Applies a force inwards, which we call friction. That's how you turn with friction. Oh, and if the wheels apply a bigger force than the road is capable of, you're going to keep going in a straight line at a steady speed. You're going to skid off the road. That's called an accident. Okay? So notice, friction is perpendicular to the direction the car is moving. This is because the turning friction is actually static friction, because the wheel isn't skidding, and static friction doesn't have to be opposite to motion, like kinetic friction is. So way back when we did friction, I said friction can resist motion, or can be in the same direction motion, or in this case, it's perpendicular to the direction of motion. Good thing, too. Artificial gravity. One method of generating artificial gravity. Oh, I like example 5, I like example 5, I like example 5, because it's cool and it's a nice question. One method of generating artificial gravity in outer space, yeah, Jennifer, would be to build a circular space station and spin it. There's a side view, there's a top view. So let's suppose we've built this space station and it's got a radius of, okay, I'm going to change this question. This is a bad example, I think. And again, let's try this again. No? Okay, pause. This is irritating me. Continue. I'm going to change the number here. Instead of having a radius of 5.2, let's make the radius 55 meters. Okay? Because I want to be realistic. What does the period of rotation need to be? Now, this is a huge space station, but this would be feasible to generate an artificial gravity of 80% of the Earth's gravitational field. So, you ready? What are the forces? Let's label the top view picture. What are the forces acting on this person? Wait a minute. Where are we right now? Space. Don't be getting no obvious one because there's no gravity out there. Okay. What else? Well, what path is this person tracing out? So there has to be a force inwards. I'm not putting Fc there. Fc does not appear on my free body diagram. What force is that? And I always pause to see who can see it. What force would we call that? That there force from the floor. In this case, the normal force is what's pushing you in a circle. And normally, we've often said normal force equals mg. Not quite. What do we want normal force to be? 80% of mg. In this case, 80% of mg. So I'm going to get this. 0.8 mg equals MAC. And yeah, a little kid would feel the same gravity percentage as an adult. Which AC do I want to use? The one with the speed or the one with the period in it? How do I know? Okay, it's talking about that. So I'm going to say then, okay, equals 4 pi squared r over t squared. They want me to find the period of rotation, how many seconds it would take for it to rotate if we wanted to have an artificial gravity. I need to get the t by itself. This is, once again, holy smokes, 1 fraction equals 1 fraction. The t moves up. The 0.8 g moves to the bottom. Now that's t squared. Halen, how to get rid of a squared? Yep. And now we're doing some space station planning. 80% gravity probably would be fairly livable. You wouldn't have all the heart conditions or all the bone density deterioration that you have in 0G. This might be what they might do, for example, if they go on a Mars mission, because they would have to have some type of artificial gravity, I think. So you spin it. It's going to be the square root of 4 pi squared. I made it a bigger space station. Can you see why? Because if it was only 5.2 meters, the period is really, really fast. It's spinning, I think it was like spinning once every second, which really doesn't work for docking and things like that. All over 0.8 times 9.8. Even this is a little fast. This would be 16.6, is that right? You would need it to spin every 16.6 seconds. So what we're talking about, we'll do this next class, but I found it, like we're talking about a picture or a space station designed like that. In the very center, there'd be very little or no gravity. It'd be weightless. But as you move further and further towards the edge, gravity would increase. Why, Mr. Dueck? Oh, because as R gets bigger, sorry, I should get the G by itself. Anyways, it would increase. We'll look at that next lesson. Okay? Pause here, finish homework from lesson 1.